Okay, so we left off with residence time on the last one. So we're going to start with a residence time problem. If you feel like you are completely comfortable with residence time and don't need to see an example, I just fast forward to the next slide. In this problem, we have a body of water with a rate of removal of magnesium, a metal, is 1.3 times 10 to the 4 kilograms per year. And there's approximately 4.6 times 10 to the 7 kilograms of magnesium. So what is residence time? Well, first thing we're going to do is we're going to check and make sure that we have the same units for each. So we have kilograms and kilograms. So we don't need to do any conversions to start with. Anytime you are using a formula, you should always write the formula. This way, on a test or an assessment, you can show that you at least understand the formula, even if you've made a small mistake with the math. So I'm going to start right here. T is equal to A over R. A is equal to amount. We have 4.6 times 10 to the 7 kilograms. The rate of removal is 1.3 times 10 to the 4 kilograms per year. Kilograms cancels out. Go to the calculator. It's like 3.5 times 10 to the 3 years, or 1, 2, 3 years for all the magnesium to be removed from that body of water. I've shown the formula, which you should do. I've shown my work, which will get you more points, and I put in scientific notation as well. All of these are necessary to get full credit for a problem. We'll work on a couple more of these as we go through, and there are also a couple in the book as well. So we've covered salinity pretty well. Let's talk about pH, another property of seawater. And is seawater acidic or basic? You should know by now that it is basic. It's basically around 8.1 to 8.3 at the surface. Not all water is basic. Volcanic lakes and acid rain both tend to be very acidic, whereas desert lakes, because they have a huge amount of salt, tend to be very basic. Remember that on the anything with a pH of less than 7 is considered an acid because it has extra hydrogen ions, and anything with a pH of greater than 7 is said to be basic because it has extra hydroxide ions. Obviously, pure water is going to be 7 because HOH, water, has the exact same ratio of hydrogen to oxygen. And remember, pH is a logarithmic scale, which means if something has a pH of 3 and something else has a pH of 4, the 4 is 10 times less acidic. It's not a 1-to-1. The carbonate buffering system is something I promise you I will ask on a test. It's really, really important. And this picture right here is in the book, and the key portion right here is going to be in here. And what this is, I guess I'll explain it first and then I'll write it again. So, you guys asked me not to use yellow, so let me try a different highlighter. How about pink? So we have carbon dioxide in the air, and due to the wave action, it dissolves in, where it mixes with water. This gives us carbonic acid, which is this substance right here. Carbonic acid is really, really important. It is a weak acid, which means it neutralizes easily. And it goes on and breaks down in water to make these two substances and these two substances. And this gets to be really, really important in terms of what we mean by buffering. Specifically, this substance right here, which is known as bicarbonate ion or hydrogen carbonate ion, has the unique ability to both take up hydrogen and give it away. And in the presence of acids, it takes up more hydrogen and goes this way and makes carbonic acid, thus neutralizing the acid and maintaining its pH. In the presence of a base, it will pop off a hydrogen, making this, and that hydrogen right here is free to go interact with the base and neutralize it, thus neutralizing the base. What does this mean? This means that the ocean is a highly, highly buffered system, meaning that it's really, really hard to change the pH of the ocean because this ion will counteract it for long periods of time. Now this image is a little complicated. There's a lot going on there, so I'm actually going to draw it again for you. And I'm going to kind of go left to right. So we have the water. We have water. And in the atmosphere, we have CO2. It's actually in much higher concentrations in the atmosphere than it is in the water. In the water, the CO2 reacts with the water. Now this arrow is going to go in one direction. And the direction of the arrows is important here. To make carbonic acid, which is H2CO3. H2CO3, and this arrow is going to go in two directions. Can ionize basically to make HCO3 minus and a hydrogen ion. The key thing here is this. This is that bicarbonate. And if you're ever asked which substance buffers the ocean, this is the one they're usually looking for. It has the ability to both take up and give off the hydrogen. Another double-ended arrow, and I wish I could draw this all straight in a row, but I can't, means that the HCO3 can give away its last hydrogen and become CO3 2 minus. And this, these arrows are important. One direction over here, two directions here, two directions here. This is the formula I expect you to know. All those other arrows showing how it reacts with sediments is fine, but for the level of this course, we don't need to know it. One of the things that you should know is that this, combined with calcium, makes calcium carbonate, which is a substance that most organisms make their shells out of. Things like oysters and other bivalves, as well as really small things such as foraminiferans and other things we'll talk about as we move on. But this formula, this chemical formula, allows the ocean to maintain its pH. So why do we care? Because the ocean is very buffered. That's what allows life to exist. It's hard to live in an acid. It's hard to live in a base. If you're at constant pH, it's much easier to make your living. And in terms of what's going on now in climate change, we are adding more and more CO2 to the atmosphere. And this introduces more and more of this acid, which is shifting the equation of the balance. I don't remember if you guys remember Le Chatelier's principle from chemistry, but it's shifting the equation in favor of the acidic side. It's expected that the pH of the surface oceans will actually be about 7.8 in your lifetime, which is really drastic if you think about how well this substance can counteract it. And that's a great concern for both organisms and people. Now, also digging way, way back to chemistry, I know, there was Henry's Law. And Henry's Law said that cold water can dissolve more gases, which was kind of counterintuitive, but we talked about how the dissolution process happened. That's why cold soda is fizzier than warm soda. So you would expect if cold water can hold more gas and CO2, more CO2 would mean more carbonic acid, that the deep ocean, because it's cold, would have more CO2 and would be more acidic. And you would expect that, except that, remember we talked about the calcium carbonate shells? They are the marine snow or in fecal pellets, or basically just settle down to the bottom of the ocean. And the shells of these dead organisms actually react with the carbonic acid and neutralize it. And it's called an antacid function in quotes. I don't really know why it's in quotes. It's literally the exact same thing as antacid. Tums is usually calcium carbonate, if you've ever had to take it. And so the calcium carbonate of those shells allows the ocean's deep waters to not be highly acidic. They're basically very similar to what it is at the surface. This is going to come into play later on. We're going to talk about what's called a calcium carbonate compensation depth, or the CCD. And this is a depth at which all the shells below it will dissolve. And you see this more in the Pacific Ocean. We'll talk about that later on. But know that the ocean is not highly acidic at great depth because of the existence of these shells to neutralize the carbonic acid. And that's where we're going to leave off for pH. Next one we'll start with surface salinity.